factorial Cn.
Yes. So now we can describe what these Cn's are. In other words, the Cn's have to be nth derivatives of A divided by n factorial. So now we have a way of getting what's called the Taylor series of a function. And we'll prove in our real analysis class that these indeed are, right, that these, like e to the x does converge to its Maclaurin series, and sine x and cosine x, right? We'll prove this in the real analysis class. For right now, I just want you to accept that they do have these expansions, but that you do understand why the pattern has to be this way. You do understand that. So let's write the result now. So what we can now say is that we can express our function. We can express common functions that we have used in this class for a long time. We can express them in our transcendental functions. We can now express them as Taylor series. So, series is going to be a sum from n equals 0 to infinity of the nth derivative of A divided by n factorial times x minus a raised to the n power. So there it is. Now if we can figure out what this pattern is, we can get a nice expression. If we can just figure out what that is. So this is going to be a kind of a find the pattern exercise. What's the pattern? So let's do some of our favorite ones that have easy patterns like e to the x sine x. Let's do e to the x sine x and cosine x. Let's do e to the x sine x and cosine x. And let's have here a is going to be 0. So let's expand them by just figuring out the pattern. So what I'm going to do is I'm going to make a column. I'm going to have a column for n. I'm going to have a column for the nth derivative. And I'm going to have a column for the nth derivative at a. In this case will be 0. So here we've got n is 0. I've got, say, let's do e to the x. I've got e to the x. I've got e to the 0 is 1. Okay, now if n is 1, what's the first derivative?
E to the x.
It's e to the x. And so it's going to be 1. So this is the easiest one because they're all going to be 1 in this column. Which means that I now know what a general nth derivative of a looks like. It's just 1. So in other words, e to the x is going to be series from n equals 0 to infinity of 1 over n factorial times x minus 0 to the n, which is going to be a sum from n equals 0 to infinity of x to the n over n factorial. So now we know a new way to write e to the x by using this pattern. So we're going to say e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus dot dot dot. Now what's really nice about this is that, let's say I went just this far, that would be called the Taylor, the 4th degree Taylor polynomial. In other words, that's an approximation to e to the x. This would be called the Taylor 4 T4. And so you're approximating x with a polynomial. You're approximating e to the x with a polynomial. The further out you go, the better your approximation is getting. So if you go out to say 17, you know, a degree 17 polynomial, you'll have a better approximation, right? But the further out you go, right, 100, 10,000, right? This is in the limit, right? This is going to be what we call the Maclaurin series. The reason we call it Maclaurin is just when it's 0, just call it Maclaurin instead of Taylor. Okay? Let's try to figure it out for sine. Yeah.
Wait, so how'd you get that series? X to the n over n factorial.
Well, because we know that this is the formula, right? And we found that all the nth derivatives at 0 are all 1. So 1 is just now this expression. The n factorial is still there. A was 0 to begin with. That's how we just got it. So as long as we can find what a general nth derivative of A looks like, if we can figure it out, then we'll be able to get the Taylor series. Let's do sine and see what sine looks like. Sine is interesting, a little more interesting, in that we get an alternation going on. So again, I'm going to create 3 columns. So now let's have f of x be sine x. And I'm going to make 3 columns. I'm going to take the n, 0, 1, 2, 3, etc. I'm going to take the nth derivative of x, and then I'm going to take the nth derivative at a. Right? This is what I'm interested in. In fact, what I'm interested in when I get, you know, like the general nth term, I'm interested in what the general nth term is down. I'm interested in how to describe this by the pattern. That's what I'm interested in. I'm interested in this row in column 3. So that's going to give me my pattern. Yeah.
Is A always 0 or?
Here it is.
Okay.
It's not always going to be.
Okay.
We'll do examples where it isn't. Just for these, because I'm doing Maclaurin now. So let's do. Let's look at the pattern. So here it's sine x. What's sine of 0? No.
0.
0. Okay, so just 0. What's the derivative of sine?
Cosine.
What's cosine of 0?
1.
Okay, what's derivative of cosine?
Minus sine.
What's the minus sine of 0?
0.
What's the derivative of this?
Negative.
Minus cosine. What's minus cosine of 0?
Minus 1.
Negative 1. You see what's happening?
Yeah.
Now the next one, the fourth, when I take the fourth derivative, I'm back to sine. So it's going to repeat. It's going to go sine, cosine, minus cosine. So in this column here, what's happening? I'm just going to get a repetition. 0, 1, 0, negative 1, and then continue. So which ones are being eliminated? Which rows are eliminated?
If you add it together?
Find the pattern for the rows that are eliminated.
The 1 and negative 1?
Hmm? Which rows are being eliminated?
Oh, 2 and 4.
2, 4, 6, evens, right?
2.
All the even rows are eliminated,
2 to the n.
and then the odd rows are alternating. Okay, so here's what we can do. We can say that sine x is equal to, so when f of x is sine x, we can say that sine x is a sum from n equals 0 to infinity of the nth derivatives of 0 over n factorial x to the n. Now we can split this series into its odd and even parts. So we can say it's a sum from n equals 0 to infinity of the f 2n's of 0 over 2n factorial. This will just be the even powers, plus we can sum over the odd powers. Now these all are eliminated, right? All of these are 0. So all of these fall away. This is all 0. So what are we left with? The odds. And what is the common expression for the general odd term? It's either going to be a 1 or a negative 1. It's alternating. Now it starts out when the index is 0, it's going to be positive 1. And when, for instance, the index becomes 1, 2n plus 1 becomes 3. So it's going to be negative 1. So the pattern that we're getting is that this is going to be a sum from n equals 0 to infinity of alternating sign x to the 2n plus 1, the odds, over 2n plus 1 factorial. So what we're getting for sine now is sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot 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 dot. That's sine. Sine keeps the odd powers and removes all the even powers. And the 7th degree Taylor polynomial is what I have there that's visible. That would be an approximation of sine. Can you, on your own right now at your desk, use this pattern analysis and try to figure out the expansion for cosine without looking it up or looking in your text? Can you give me the Maclaurin series for cosine? You want to figure out the pattern in this column. This is the column that, column 3, you want to get the pattern. Okay, what's the pattern?
It's the alternating,
It's alternating
of x
form.
to 2n.
Yes.
And then 2n.
Yes, that's exactly right. Yeah. So when you do cosine, you realize that the odds all fall off and the even powers stay. And that's exactly right. So cosine cosine is going to be a sum from n equals 0 to infinity of alternating sign x to the 2n over 2n factorial. In other words, it's going to be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial dot 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 dot. Okay, with that. That's cosine. Cosine works with the even powers. Sine is the odd powers. Do you remember way back when, with the differential equations, it's kind of revealed a mystery. So remember way back when, with the differential equations, that so when we had the second degree linear homogeneous differential equations that were ay double prime plus by prime plus cy is 0, and we took ar squared plus br plus c is 0, and we got to the situation where in case 3 we had, so remember our case, in case 1 we had 2 real roots, and we just took y to be some constant e to the r1x plus c2 e to the r2x, and then we had case 2 where we had a repeated root and we had this c1 e to the r1x plus c2x e to the r1x, and then we had this case 3. And this case 3 was we had roots alpha plus minus beta I. And I told you at that time, just say this is e to the alpha x and a c1 cosine beta x plus a c2 sine beta x. Well, sort of where that's coming from is you're going to have this e to the alpha plus minus beta I x, okay, and you're going to get this e to the alpha x, and then you're going to be multiplying by this e to the beta I x, okay. So what's happening with that? Well, let's expand this as a series. So let's look at this. Let's look at this e to the beta I x as a series. Well, it's a series from n equals 0 to infinity. Well, what can I do? I can write this as let's do the odd powers and let's do the even powers. So in other words, I can make this a x to the, we know the whole thing is just going to be this beta I x to the n over n factorial. But I can split this up, right? This is just going to be beta x to the n. You're going to have this I to the n, and you're going to have this n factorial. Now, what happens with I to the n? Let's look at what I to the n does. So what happens? You're going to have, it's going to start out, right, at, so here's your n column, right? So I to the 1 is when it's just going to be I. When it's 2, what's it going to be? It's going to be -1. And when it's 3, it's going to be minus I. But when it's 4, it's going to be what? I to the 4th is back to 1, right? So what's happening is it's going to be going, on the odds, it's alternating with I and minus I, and on the evens, it's alternating with -1 and 1, right? Okay, and at 0, I to the 0 is just 1. So it's going 1, -1, 1. So you see what's happening is we can rewrite this in terms of even and odd. So if we rewrite this in terms of even and odd, what we're getting is a sum from n equals 0 to infinity. We'll do the evens, which is going to be the beta x to the 2n over 2n factorial with these I to the 2n's. And then we'll add in the sum from n equals 0 to infinity. I hope they can see me. It's beta x to the 2n plus 1 over 2n plus 1 factorial. And we have these I to the 2n plus 1s. But that's sine and that's cosine. That's where that's coming from, right? That's sine. So in other words, what we're getting is we are getting the cosine. We're getting the cosine of beta x, and then here we're getting I, and we're getting sine beta x, right? Because we're taking this I out. We're getting the alternating sign, yeah? So that's where it's coming from, right? Because this is just, in other words, this is just an alternating sign. This is just an alternating sign of -1 to the n, and this is an alternating sign -1 to the ni. In other words, I to the 2n is just an alternating sign, and then I to the 2n plus 1 is just an alternating sign with I. And that's why you're getting the cosine and the sine, right? Now then we throw in those constants. In other words, we work this out so that if we have a complex constant that we can throw in, when we multiply a complex constant by I, some of them will just become real, so we're only interested in those real ones. So that's why we say C1 cosine beta x plus C2 sine beta x. Okay, this is a justification where this is coming from. So it's coming from the expansion of sine and cosine, where cosine is handling the evens and sine is handling the odds. This is kind of fitting it together nicely. Yeah. Does everyone see that? So maybe I did it too fast. So this one right here is just, this one right here is just going to be a sum from n equals 0 to infinity of beta x to the 2n over 2n factorial, and that's just going to be an alternating -1 to the n. And then this one is going to be, then we're going to be adding in the sum from n equals 0 to infinity of beta x to the 2n plus 1 over 2n plus 1 factorial -1 to the n. We can put the I out front. Now you recognize this, that's just your sine beta x, and that's just your cosine beta x. That's just plugging in beta x for the variable in the Maclaurin series for cosine, and that's plugging in beta x for it, right? So this is just sine. This is just sine beta x, and this is just cosine beta x. That's where that's coming from. Okay, so that's kind of a justification. That ties up a loose end. It's tying up a loose end, I told you right. Yeah.
But how do you go from y double prime plus y prime plus c to e power alpha plus minus beta of I?
Mm-hmm.
Like, you know the first step? How did you get there? That
From where?
E alpha plus or minus b, or beta of I.
Oh, well, this is just, I'm just doing the plus one. and then just to illustrate it, and that's just algebra.
No, I mean before that.
What do you mean?
How'd you go from that form, y double prime plus y prime plus y? to
Oh,
that?
this?
Yeah, to that.
Oh, because remember when we wrote these out in columns and were showing it, we said assume the solution was an e to the something, and we took the derivatives and we kind of showed the whole justification. So we said it would kind of fit, right? It kind of fits like why we justified all these. Like we went through with columns and we kind of proved these first two, or I think I signed this for extra credit. I proved this one and I assigned this for extra credit. And then we'd say, well, it would fit, it would kind of be nice, consistent with our theory if we also, once we got these roots, if we just considered e raised to the power of those roots times x, it would be consistent with our first two steps, and the curiosity is why is it cosine and sine?
Okay.
And then that's kind of tying that in. Okay? Okay. So let's try one. We're going to try one. So we're going to try it. Find the pattern. So let's do one. And this is all just pattern analysis, basically. Yeah, let's do root x. Let's do a equals 4. So here we're not going to do a equals 0. Let's do root x. So square root of x, a is 4. I want you to write root x as a sum when an f of x is root x. I want you to write root x as a sum from a equals 0 to infinity of an nth derivative of 4 over n factorial times x minus 4 to the n. I want you to get the Taylor series centered at 4. And all you have to do that, because you know the theory tells us it's going to be an nth derivative of 4 divided by n factorial. All you have to do is figure out what this pattern looks like. What is an nth degree? What is an nth derivative of 4 divided by n factorial? So all what I want you to do is write your 3 columns. In other words, here's your n, and you go 0, 1, 2, 3, 4, etc. And then here's your nth derivative of x, and you go etc., 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 etc. And then here's your nth derivative of 4 column, and you go function, first derivative, second derivative, third derivative. And what you're trying to find is what is the general nth derivative of 4. See, if this is n, your general like nth row. You're trying to figure out like, what is this? And if you figure out what that is, you can just plug it in there and you'll have the answer.
For the second one, we plug in root x for x.
Yeah, so this is, so the function itself, in other words, just the function itself is root x. And then the square root of 4 is 2. So the square root of 4 is 2. So now what's the first derivative of root x?
1 over 2.
1 over 2 root x. So this is 1 over 2 root x. What is this? 1 over 2 root 4, or 1 over 4. Okay, what's the, and so we'll do these in, let's make some nicer rows. So now at 2, let's try to fill this in. What is the next derivative? And maybe it's best to write this as 1/2 x to the minus 1/2. What's the derivative of this? Let's keep it in this form.
Negative 1/4 x to
Okay.
the
1/2, another 1/2 with a negative sign and an x to the
negative 3/2.
-3/2. Now, it's going to help you, so if you call this 1/4. That's correct, but it's going to help you find the pattern if you don't simplify it. So write it out long, it helps you figure out the pattern. So this is going to be minus a half, x to the minus 3 halves. So now we're getting minus a half, x to the 4 to the minus 3 halves. Okay, so we're making progress. Okay, what if we differentiate this? Let's try to differentiate that. What do we got on this third row? Let's differentiate this. What are we getting?
So it's negative half.
Negative a half, negative 3 halves, right? X to the minus 5 halves. Okay, so the negative is going to be positive. So now, don't we see this kind of an alternating sign? There's some kind of alternation going on here. Now, I think we can call this 2 to the third, 1 over 2 to the third. So what I'm seeing in this piece right here is I'm seeing a 1, but there's going to be a negative, right? There's a negative, that's canceled. So I'm seeing a 1, 3, 2 cubed, and now I've got an x to the minus 5 halves. So what I'm looking at is a 1 times 3, and now I've got a 2 cubed x to the minus 5 halves. Okay, I think we're getting a feel for it. Maybe one more and you might see it. Okay, so let's do one more row. Let's differentiate this. What's going to happen? The negative 5 and the 2 negatives is going to become negatives. It's going to be negative. It's going to go 1, 3, 5. We're going to have another 2 down here, so it's going to be 2 to the 4th, and it's going to be x to the minus 7 halves. Okay, does everyone see that? So it's going to be a negative 1, 3, 5, and it's going to be 4. This should be a 4. It's going to be a 4 to the minus 7 halves, and then it's going to be a 2 to the 4th. Okay. So I think we're ready to, we got to find what's right here. So I think we're ready. So let's now try to figure it out. What happens when it's n? What's the pattern? Let's go through the pattern. When it's a 4, it's a 2 to the 4. When it's a 3, it's a 2 to the 3. When it's a 2, it's a 2 to the 2 in the denominator. So when it's an n, what's in the denominator?
2 to the n.
2 to the n. That's obvious pattern. So we got 2 to the n. Okay. Now, when it's 2, it's negative. When it's 3, it's positive. When it's 4, it's negative. So which ones are having the positive? The odds. So we want odd to be positive, even to be negative. How do you express that? Minus 1 to the what? Minus 1 to the, not n. No. Minus 1 to the n does the opposite. It gives you negative on odds and positive on evens. You want the opposite. So n plus 1, yeah. So minus 1 to the n plus 1. Okay, so we've taken care of this. Now we've got to figure out the rest of it. We only got two other things to figure out. We almost got it. So let me get my blue. My blue marker is in here somewhere. Okay. So now, what are we doing? We're going 1, 3, 1, 3, 5. The next one is going to have a 7 when we differentiate. It's going to be a 1, 3, 5, 7 when we differentiate this. What are we doing? We're multiplying odds, right? Okay, so we're just multiplying the odds. We want to figure out where are we stopping in relation to what row we're on. So when we're on, for instance, row 3, we go 1, 3, we stop at 3. When we're on row 4, we go 1, 3, 5, we stop at 5. So I want to find the pattern of where we stop on row n. If 3 goes with 3 and 4 goes with 5, what does n go with?
Is it like 2 to the n?
Not
Minus-
to the n, but 2n,
Minus 1,
2n minus,
2.
2n minus,
2, wait, what is it? 2n minus 2 plus 1.
2n minus 1.
2n minus
3.
3.
3.
2 times 4 minus 3 is 5. 2 times 3 minus 3 is 3. 2 times 3 minus 3 is 3. 2 times 4 minus 3 is 5. We're stopping at 2n minus 3.
Okay.
Yeah? So 3 goes with 3, 4 goes with 5, n goes with 2n minus 3. Doesn't that make sense? We're multiplying by 2 and subtracting 3, that's the pattern. So we're going to say that here, what are we getting? We're getting a 1, 3, 5, dot, 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 and we're stopping at 2n minus 3. Okay, and now we just got to figure out the 4 part. Now it's going to be 4, and we're always going to have the raised to a power where we're going to have the 2 in the denominator, but we got to figure out it's going to be a minus something. We got to figure out what this is. Now we have another pattern. So now when it's, I'll do this one in black. So when it's a 4, we have a 7, and when it's a 3, we have a 5, and when it's a 2, we have a 3. So now we're getting the pattern 2, 3, 4, 2, 3, 3, 5, 4, 7. So when it's n, what are we getting? 2n minus 1. Yeah, this is pattern recognition here. So this is a 2n minus 1. Now we have it. All we have to do is take this and throw it there. We've got our answer. So in other words,